Let's get started. In this lesson we are going to discover the soft pin constraint and do various manipulations with it. Now I'll show you what example I have prepared and then let's get to work. See, the torus move up and down along the y-axis. And for this I use the noise that is in the library of Motion FX. Here is the noise. Okay, after the animation comes the basic vellum setup with default settings. Now let's pin the top points so that they follow the animation. To pick up the animation, we need to check the Match Animation option. And then select the soft pin. I will also increase the bend stiffness to its maximum to prevent the torus from bending. The last thing we will do before running the simulation is to turn on the pin constraint visualization. So, let's check what we have now. See, now the soft constraint behaves exactly the same as the first two types of hard constraints, that is the pinned points 1 to 1 repeat the movement of the target positions. Okay, to see the difference between soft and hard constraints, let's reduce the stretch stiffness, which is also the stiffness of the soft pin constraint. Take a look, they have already begun to move slightly away from target positions. Let's get closer to see better. When we specified the soft pin, a zero-length constraint was created between the points and their target positions, and since we have reduced the stretch stiffness value which is also the stiffness of soft pin constraints, they also began to stretch. To make the pin constraints primitives more visible, let's change their color. I also want to increase their radius. Good, let's run the animation and look again. Now it is much more noticeable how the pinned points move away from the target position. If we further reduce the stretch stiffness, then they will further deviate from the target positions. See, the soft pin constraints began to stretch more, and of course along with this the torus also began to stretch strongly. But what if we only want to adjust the pin constraint stiffness without allowing the torus to stretch? Well, now I will show you how it can be done. Let's set the stretch stiffness to maximum, then drop down the vellum constraint property node and insert between this two. This node is the SOP version of the vellum constraint property, which we have used many times within the DOP network. If you just need to edit some constraint properties and you are not going to change them during simulation, then it would be more correct to do it through this node at the SOP level. Okay, now we need to specify the constraint which properties we are going to change. Look, there are only stretch and bend, but we need to specify the pin constraint. So how do we do this? Well, for that I suggest opening the geometry spreadsheet and taking a look at the constraints types. Let's hide all attributes, then show the only type. See, beyond the distance and bend, there is also a pin, and we can use this attribute to refer to pin constraint and modify its properties. So, in this group line, let's type the following. @type is equals to pin. Now we can override the stiffness value only for the pin constraint. The factor of 1 is fine, let's check what we get. You see, now the torus does not stretch at all, but the pin constraints stretch decently. Besides stiffness, you can override any attribute you like. For example, let's override the damping ratio. Look, it is no longer so springy. In case you need to detach the torus at some point, you just have to delete the soft pin constraints. The vellum solver will delete all constraints that have the remove attribute set to 1. See, the torus began to fall as they were removed. Of course, if you make it 0, the solver will not remove them. To break the pin constraint at some point, you just need to change this attribute from 0 to 1, but of course this must be done within the DOP network. Now we will delete this vellum constraint property, then dive into the dynamic network and create a new one. Connect to the force output and then specify the pin constraint. At type is equals to pin. Override the stiffness with factor of 1. And activate the remove attribute and set it to 0. Then we will use the vex expression to make it 1 at some point. Let's type the following. If the current frame is greater than 65, then the remove attribute is set to 1. Well, now let's check what we get. You see, after frame 65, the constraint is removed. Let's change the breaking frame and look again. That's it, let's move on. Now I want to show you one problem that you will face if you manipulate the properties of the pin constraints in this way. Let's deactivate the vex expression and disable the remove attribute so that the constraint is not removed. Then go to the constraint properties, turn on the plasticity, and see what happens. As you can see, plasticity also affected the pin constraints because all the attributes that we haven't overridden will still inherit the stretch constraint properties. It turns out that you need to override all common pin constraint properties so that this does not happen. Now the plasticity will not affect pin constraints as we override the plasticity properties. Well, so as not to take these extra steps every time, you can simply create a separate pin to target constraint which will not inherit the distance constraint properties. Drop down the vellum constraint node. Insert between these two. Then make it the pin to target constraint. So, before we specify the points we want to pin, let's go back to the cloth constraint and remove all previous pins. As well as disable the plasticity, since we don't need it anymore. See, until we have specified any points for the pin to target constraint, it pinned them all. Let's pin the same top points again. Good, now we have to change the pin type to soft. Look, once we have specified soft pin, the stretch and bend constraint properties became active. The bend constraint only affects the orientation and we will study the orientation pin types when we deal with hair constraint. So for now I will just turn it off. Now let's reduce the stiffness, check match animation option, and see what we got. As you can see, we got the same result, but now the soft pin constraint has its own properties and does not depend on distance constraint. It turns out, we can output a group for the pin constraint and use it inside the DOP network to modify its properties. So, let's dive into the DOP and then create the vellum constraint property node. Connect to the force output, then specify the group that we created for pin constraint. Everything else is the same. The only difference is that now the pin constraint does not inherit the cloth distance constraint properties. So, let's check what we get. That's it, after frame 60, the pin constraints are removed. Well, let's move on. Now I want to show you another interesting method to break them. Let's delete this, then get out of the DOP network and look at the pin to target constraint properties. See, there is a section for breaking constraints. When this option is enabled, the constraint primitives can be removed by the solver when sufficient deformation or stress is applied. Here you can specify the attribute that the solver should use as a trigger to remove primitives. And this is the threshold after which the break will occur. Now let's set 0.8 for the threshold and see what we get. You see, as soon as the stretch stress exceeds a given threshold, the pin constraint is removed. Okay, let's increase the threshold a little and check again. Now the pin constraint is removed a little later. The constraint primitives are removed at the same time because the stretch stress value is the same for each primitive. Now let's pin more points so that the stretch stress is unevenly distributed between the primitives and they are not removed at the same time. Since they have become more, the stretch stress in each of them has decreased, so the threshold should be lowered. See, now they began to remove one after another. Okay, let's increase the threshold a little so that they don't remove so quickly. Here we go. As soon as the stretch stress exceeds the specified threshold for some primitive, it is removed immediately. To make it clearer, let's visualize the stretch stress of pin constraint and look again. Turn off display geometry so that only the pin constraint displayed stretch stress attribute. Then adjust the max value close to the threshold to get correct visualization. There you go, now you can see by color where there is more stress and where less. Let's watch it again. Okay, we can move on. See, in addition to stress you can also use stretch distance and ratio. If necessary, you can use custom point attribute to vary threshold values. And they can also be animated using the vellum constraint property node. Here they are, the break threshold and the break type. Okay, let's go ahead. Now I want to show you one interesting parameter of the pin to target constraint that is not present in the distance constraint properties. It is a velocity blend parameter that can be useful to you quite often. To demonstrate this parameter, I also prepared a separate example file. Let's switch there. Okay, let me quickly show you what example file I have prepared. I just use a bend deformer to bend the plane back and forth and animate the angle with motion FX wave. Then I created a mask which we will be using soon to scale the velocity blend parameter. The range of mask is from 0 to 1. I just use the relative to the bounding box information along the y-axis. Okay, let's turn off the mask visualization for now. Then comes the basic vellum setup with default settings. Let's play and see. It just falls under the influence of gravity. Now let's create a pin to target constraint to attach the cloth to the animated geometry. Select from here the pin to target, then specify it as a soft type and check the match animation. As for the orientation, just turn it off. See, now absolutely all points are attached to the target geometry. That is, if we now run the simulation, they should follow the target geometry. Here we go, the cloth follows it completely. So now let's use the mask to scale the stiffness of the soft pin constraint. Well, let's see what has changed. You see, the tip of the cloth already freely dangles because there the stiffness of the pin constraint is closer to 0. Let's scale down the mask attribute to give the cloth more freedom. As you have already noticed, the cloth's tip got a lot more freedom, but I want to make it even more. So let's scale down further. Well, now I'm happy with this, but I want to edit the mask a little. Let's turn it on to visually see the changes that we will make now. Then go to the attribute VOP and start editing this spline ramp, which defines the transition of the mask from 0 to 1. That's better. Only the base will closely follow the animation, and the rest will tend to the target geometry weakly. Okay, I am completely happy with this result, let's move on. Now I am going to enable the velocity blend option that allows us to blend in the velocity of target geometry, but this requires the target to have a v-point attribute to provide the local velocity. So let's create it. Drop down the point velocity node and add it after deformation. The point velocity SOP computes the velocity attribute from the deformation. Okay, now we can add some percentage of this velocity to the system. So, a blend factor of 0.1 will mix in 10% of the target velocity in a standard frame. Well, let's check what has changed. Now the simulation velocity is 10% closer to the target velocity. To make it clearer, let's increase the blending factor and check again. You see, the simulation has become even more restrained since 20% of the target velocity affects it. If the target geometry does not have a velocity attribute, the velocity blend will blend to zero, which will reduce the overall velocity. That is now, the simulation velocity dampened by 20%. Okay, let's enable the point velocity node again, then decently increase the blend value and check the result. Look, in addition to taking 50% of the target velocity, the simulation is also affected by the attachment force of pin constraint. But what if we reset to zero the attachment stiffness? Well, then only the effect of velocity will remain. Now let's adjust the mask attribute so that the stiffness goes to zero everywhere except the uppermost region. That's it. The soft pin attachment force will only act in the red region. Okay, let's check what we got. You see, the simulation is only affected by the velocity of the target geometry, and therefore it has become very similar to the target animation. Good, now I propose to distort the velocity vectors of target geometry by adding noise to them and see what happens. Look, there is a curl noise tab in the point velocity properties. Let's enable it to add noise to existing velocity vectors. So, let's check what we got. Here we go, the noise has already entered the simulation. To firmly secure the pin constraint attachment to the top, let's set the mask multiplier to 1. See, the topmost region no longer swings up and down. Of course, if you want to reduce the impact of the target velocity, you just need to decrease the blend factor. You may even not use the attachment force at all by zero-outing stiffness for all points and use the pin-to-target constraint to bring only the target velocity into the system. Okay, since it will now be free-falling, let's turn on the ground plane and see what happens. Look, now the cloth is not tied to the target geometry in any way but still depends on its velocity. Using this technique you can make interesting simulations. Okay, that's all for this lesson. We've completely dealt with the pin-to-target constraint. All other parameters are already familiar to us from the previous lessons, so let's end this lesson with this. In the next lesson, we will already talk about the drag force, which has an important role on the cloth simulation. See you in the next lesson.